Hello everyone. Welcome to this video on overfitting and cross-validation. I'm going to start this video with several important concepts: training data, testing data, validation data, training error, testing error, validation error, and generalization error. Training data is the data used for training a machine learning model. In training data, all instances have labels. Error of the trained machine learning model on training data is called training error. Testing data is the data used for testing a trained machine learning model. Labels of all instances in testing data are unknown beforehand. Error of a trained machine learning model on testing data is called a testing error. Apart from training and testing data, another kind of data is validation data, which are used for evaluating the quality of the trained machine learning model. Like training data, all instances of validation data have labels. Error of a trained machine learning model on validation data is called validation error. Generalization error is the testing error of a trained machine learning model. It describes how well a trained model performs on new incoming data, which can be estimated by validation error. Overfitting is a phenomenon of training a machine learning model. Overfitting happens if training error is very low, but testing error is high, and there's a big gap between training and testing errors. In this example, overfitting happens because training error is 0 and testing error is 30%. Detecting overfitting of a trained machine learning model is quite straightforward. You can compute the gap between training and validation errors. If this gap is large, overfitting happens. You can also slightly increase the weight of regularization term and check how validation error changes. If this increase leads to smaller validation error, that means overfit happens. The final approach is to compare number of variables to number of instances. Overfitting has a higher probability to happen if number of variables is greater than the number of instances. In this case, you have to put a large value to the coefficient before generalization term in the objective function. Overfitting can be explained by fitting noise, bias variance trade-off, and generalization error bound. First, overfitting can be explained as fitting noise. Dependent variable is usually composed of signal and noise components. A well-trained machine learning model should detect noise components successfully and run training process to fit signal components. Overfitting happens if the model fails to detect noise component well. It is complex enough to fit the sum of both signal and noise components. Here is an example. No overfitting happens if there is no noise term. Adding some Gaussian noises to dependent variables will incur overfitting of training the machine learning model. When overfitting happens, the trained model fits the sum of signal and noise components perfectly, but it's far from its true model. The second explanation about overfitting comes from bias variance trade-off. According to bias variance trade-off, quadratic error of a trained machine learning model f of x hat can be decomposed as the sum of bias square and variance. F of x hat is the model trained on a given training data. F of x is the true model. Expectation of f of x hat is the exception function of f of x hat with respect to different training set sampled from D. This figure shows the relationship between model complexity and model bias and variance. When model complexity increases, variance of the trained model also increases. Overfitting happens when model complexity increases up to a certain value that dominates the quadratic error. Overfitting can also be explained by generalization error bound. Based on generalization error bound, training error will keep decreasing, but generalization error bound will decrease first and become increasing finally when model complexity comes up to a certain value. This certain value is the threshold value of overfitting. Many approaches have been proposed to avoid overfitting in training machine learning models. Here, I'll describe 5 commonly used approaches. Those are regularization, feature selection, bagging, dropout, and early stopping. The first approach is regularization. Its basic idea is to add regularization terms such as L1 norm or L2 norm to objective function that will bias to simple models. Based on generalization error bound, simple models are more robust to overfitting and usually have better generalization ability. The second approach is variable selection that is a pre-processing step of a machine learning model. It selects a subset of relevant variables and discards all other irrelevant and redundant variables. A machine learning trained on these selected variables is more robust to overfitting because it removes noisy variables and also decreases model complexity. The third approach is the bagging technique. The bagging technique is known as a generic approach for decreasing variance of a machine learning model. Its basic idea is to train multiple strong models on different subsets of all instances or subset of all variables, and results coming from different models will be voted or averaged as the final output. The bagging technique can avoid overfitting as it decreases variance and bias-variance trade-off. The fourth approach is dropout, which is widely used in training deep neural networks. It was known that dropout can avoid overfitting because it performs like bagging of multiple neural networks, which decreases variance and bias-variance trade-off. Dropout can also be viewed as performing like adding L1 norm regularization, which will bias to neural networks with sparse connections. The last approach is a very generic and also useful trick for training machine learning models. That is, early stopping. For most kinds of machine learning models, using gradient descent optimization method, we can stop running gradient descent earlier before it converges to a local optima. Early stopping can avoid overfitting, as it can avoid fitting noise. The problem of early stopping technique is that it is hard to determine when to stop. As described before, generalization error of a trained machine learning model can be estimated by its validation error. The validation technique is proposed to estimate generalization error by its validation error. The validation technique is proposed to estimate generalization error by its validation error. The validation technique partitions all labeled instances into training and validation groups. All labeled instances in the training group are used for training, while the other group, that is, the validation group, is used for estimating the generalization error of the trained machine learning model. The estimated generalization error is very useful for model selection and hyperparameter tuning. One disadvantage of partitioning all labeled instances into training and validation data is that less labeled instances will be used for training, which will in fact decrease the accuracy of the trained model, because less training data usually means worse trained machine learning models. One feasible approach to solving the problem of less training data is cross-validation. The cross-validation technique divides all labeled instances into k segments and rotates through using any one segment as validating and all other segments as training. All k validation errors are averaged as the final estimation of generalization error. Popular cross-validation techniques include k-folder cross-validation, leave one out cross-validation, and leave p out cross-validation. Here's an example of 5-folder cross-validation. It partitions all labeled instances into 5 segments and runs training and validation processes for 5 rounds and returns their average result. Please feel free to get in touch if you have any questions. That's it for today. Thanks for joining us.